by which we can draw the image of any object by using lens. We can also use our other source, uh, like a camera or single camera or multiple camera. All camera are uh, are based on the same principle. So I have written here, when two or more rays of light meet at a point, an image is formed, that I have shown in this figure. When these two or more than two lines meet at some place, then it forms the image of that object. And we know various has transformed into an entirely new field, that is called digital image processing, where sampling and quantization techniques are applied to convert the image into its discrete form. This is the main concept. This is our object, and this object will to get the image of this object, we will use different process, that is called sampling, quantization, uh, to convert this object in to convert this image of this object. First we get the image of this object, and after getting this image, we convert this image into discrete form. There are two types of values, like 1 2. These are the discrete value, because there are a number of points between 1 and 2. Between 1 and 2 there are 1.1, 1.2, 1.3, 1.11, 1.11, 1.12. So there are a number of points between A and 2. If we take the all points, then it is called continuous. But if we take the only integer points like 1, 2, 3, then this type of concept is called discrete. So first we produce the image of the object by using some technique, or by using some sensor, or by using camera, single camera or multiple camera, colorful camera or monochrome camera, etc., or even our human eyes. So after getting this image is converted into discrete form. This process of conversion is collectively known as image digitization. To conversion of this image into discrete form, we use the process image digitization. After digitization, the image is readily available in a form suitable for further processing by digital computers. As we know, computer works in the form of 0 and 1. So first we take the object, then we produce the image by using some sensor or some source of camera, source of device like camera, single camera, multiple camera, human eyes or other eyes. And after getting this image, we convert this image into discrete form. This image is converted into discrete form by the process image digitization. And after digitization, we get the value of this image in 0 1, and that 0 1 can be processed by the computer. So this is the basic funda of the image processing. We need to convert the object into image, and this image will be converted into digital form, that is in 0 and 1. This 0 and 1 is the discrete form, because there are a number of points between 0 to 1. So this is called discrete number, and due to this discrete number, it is known as a discrete form. After digitization, the image is readily available in a form suitable for further processing by the digital computers. If this object is converted into 0 1, then our computer can understand what is the meaning or concept of this object. An image is a projection. Now we will use projections. How we will get the image? I have just discussed uh, two main projections, that is perspective projections and um parallel projections. By using all those technique, uh, we form the image of the given object. After getting image, we will convert or digitize this image into 0 and 1. That is called discrete form. An image is a projection of the environment under consideration. If the environment is 3D, then its projection will be in 2D. uh, if we use 3D projections, if our object is in 3D, then its projections will be always in 2D. And if our object is in 4D, then the projection will be in 3D, one less than the object dimension. If object is in n dimension, if object is in n dimension, if object is in n dimension, then its image will be in n minus 1, one less than the original dimension. So this is the relation between projections. The 2D image of the image of 2D object will be in one dimension. The image of 3D object is in 2D, and for 4D it is in 3D, and if it is n, then it is n minus 1D. If we have an n dimensional space, that is this one case, if our image or sorry object is in n dimension, then its projections will be n minus 1 dimensions. Magnetic resonance images and computerized tomography images, which are 3D images, are mathematically represented by 3D functions. And this image, 3D image, will be represented by a function, and that function is denoted by f, and the number of dimensions that are used for this to represent this image. If three dimension x, y, z are taken, then the parameter of this function will be x, y, z, where x, y, and z are spatial coordinates that may represent the amplitude or intensity, the amplitude or intensity of any other parameter of the image. We will see what is the meaning of this intensity after some pages. A digital image is defined as a 2D discrete signal. This 2D discrete signal, and on this basis, there are two type of signal: 1D signal and 2D signal. And the question will be arise on these topics. One, what is signal? What is the shape of 1D shape and 2D shape? 1D signal or 2D signal? The digital image is defined as a 2D discrete signal that varies over the spatial coordinates x and y. If we are using 2D discrete signal, then there will be two coordinates x and y. If there are 3D discrete signal, then we will use x, y, and z coordinates, etc. And can be written mathematically. This 2D discrete signal will be written like this: f x comma y. It is also an n cross n array. If the size of this x is n, maximum size, and the maximum size of y is n, then we can say it is a n cross n matrix. On and this n cross n matrix can be represented by two-dimensional array, and the size of that array will be n cross n array of elements, and each element represent the sampled intensity. What is sample intensity? We will see shortly. In general, the image fxy is divided into x rows and y columns. The coordinate ranges are x from 0 to m minus 1 and y from 0 to n minus 1. The image can be written as a mathematical function of xy as given below. So our image is in the form of 2D matrix, or in n cross n. So if the x is of m values, the maximum value of x is m and the maximum value of y is n, then there is a m cross n array, and that array is 0 0 0 1 0 2 0 to n minus 1, 1 0 1 2 and up to 1 n minus 1. And in column we can write m minus 1 comma 0, m minus 1 comma 1, and last cell, this is our one cell, this is our one cell. Similarly, there are a number of cells. This is our cells. And the number of cells are equal to the multiplication of m and n. So this is our 2D dimension, and each cell is an element. Each cell is an element, and the whole elements are denoted by a function that is fxy, or it is also known as a image. And this image has two different things. First, the amplitude and the and its brightness or intensity. If object is placed at this place, suppose I have taken this example, this is our t, and suppose this t is an object, and this t is placed in a system that has different types different number of rows and columns. So if we show the number of rows and columns, so it will look like this. And the place where this object is visible will be taken as 1, and the place where the part of this object is not visible, that is not part of this cell is not part of this object, that will be denoted by 0. So if we divide this object systems rows and columns like this, then this will look this like this. This is our two-dimensional array, and place where object is present is denoted by 1, and place where it is not available, the part of that cell is not part of that object, then that is denoted by 0. If we convert this concept, or we take this value 0 and 1, if we take this value 0 and 1, then this portion will be denoted by 1 1, and this is also denoted by 1 1, but the rest portions are denoted by 0 0. So this is the value where object is denoted, and this 1 1 is denoted by some color or some intensity. It is at this place it is in black color, but if you are using a color camera, then it may be in other column other color, like this. That this is in red color, this is in green color. So this is our one of the, at this place the color is light, but at this place it is dark, and at this place the color is very high, very dark. So this equation, this cell, sorry, this single cell, this single cell is known as a image element, and this image element is denoted by f00, and this f00 value is 0. From this figure, if this cell is denoted by element image, and then this element image, or the image of this element F00 has the value 0, but the element at this place has the value 1. And this is the value of this element, this cell element. But what is about the color? At this place, color is very dark, but in other figure, this is less dark than this one, and this one is more less dark than this original color. So we need two different values to store the element value. This is our element value, that is if the mm, cell number of this is 0 1 2. If this is F2, row number 2, and column number 0 1 2, so it is at 1, so this is 2 1. This is cell element F21, and it has the value 1, but its intensity at this place is less than the intensity of this place. And the color at this place is black. So we will store the different values related to this cell element. So this cell element has a number of information. First, it has the value 1, and its color is black, and the intensity of that color is denoted by, suppose it is I2. At this place, the intensity of black is I1, suppose, and at this place it is I2, and at this place it is, suppose, I3. I1, I2, I3. So according to this, the intensity of that element is 3. Similarly, we store the all information related to each element of this n cross n matrix image. We store all these values for this cell, 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 for this cell. So we store cell element. These are our cell element or image element. There may be more other different values for this cell element. So in general, the image fxy is divided into x rows and y columns. The coordinate ranges from x to m-1, y to n-1. The image can be written as a mathematical function. For 2D image or 2D discrete signal, we will use fxy. For 3D, we will use 3xyz. That is the value of that cell. Now, we analyze this figure. In figure B, the elements are shown as either 0 or 1. The cell elements are shown with value either 0 or 1. This 0 1 are discrete value. So we convert the given image in a discrete form by digitization, which represents the value of the function, and that cell element has some values. Each element is known as a pixel. This is also known as a cell, or in computer we know it as a pixel. It is known as a pixel. That is picture element. We can also say this is our picture element. They represent the discrete data. Discrete data, I means either 0 or 1 of any digital image, and serves as the actual building block of digital image. So you can see here, if we store all these values that I have just discussed, if we store all these values at each cell, then you will get this type of figure, and this figure shows that this is the image of this given object. This is the concept, or this is the way to digitize the image in discrete format. They represent the discrete data. They represent the discrete data, either it means either 0 or 1 of any digital image, and serve as the actual building block of digital image. The value of the function fxy at every point indexed by a row and a column as a number, and has no units. Row and number has no units, and it is known as the gray value. It is known as the gray value of the intensity of the image at that point. So each cell element has some gray value that is in form of 0 and 1, and that cell element has some also intensity, and it has also some other attribute like color or security. Maybe sometimes you can you want to blur this value, so this is also one attribute, and you have to store this information for this cell element, like in password. So from figure B, the number of rows in a digital image is called vertical resolution. Number of pixels in rows is called resolution, and the number of columns is called horizontal resolution. We shall discuss about these concept of image resolution, and I have mm, defined the resolution in the first class. The number of pixels of the image is called resolution, and if the resolution is high, then the quality of image will be high, otherwise quality will be reduced. Later in this unit, the number of rows and columns describe the dimension of the image. The image size is often expressed in terms of rectangular pixel dimensions of the array. Image can be of various size, like 256 by 256. It means there are 256 different columns and 256 different rows. 512 by 512. Nowadays, the monitor has generally 1024 rows and 1024 columns. So the number of pixels will be 1024 into 1024. If you multiply these two, then you will get the resolution for this monitor. If this value is increased, then the quality will be high, and if it is reduced, the quality will be reduced. So second term, we will use image acquisition. According to the fundamental concept of optics, when two or more rays of light meet at a point due to reflection or refraction or any other phenomenon, an image is formed. The information about happened phenomenon is recorded or acquired by the respective sensors. So sensors or some other device will be used to capture the image of the object. The process of capturing real world image and storing them in a computer is called image acquisition. Uh, the notes are generally asked uh, in university examination on what is acquisition. So this is the definition about the acquisition. And I have shown this figure, and I have also described this figure, so there is no need to describe again. Now, uh, how do we get the image in digital form? This is the main question. How we will get the image of in digital form? The sensors are actually, this is our main part, and at this sensor there will be eye. You can correlate it with your eye also, and camera, single camera or any other camera, maybe a sensors, are actually the electronic devices that tap or capture the various types of signals like thermal signal, optical, electromagnetic, or any other type. Generally, the data is gathered in analog form, which is digitized through the digitizer. This digitizer will digitize the image in 01, and this digital signal is finally utilized by the digital computer for its processing. In analog form, the storing of information or data is costlier than the digital image or digital data. So we need to convert all data in the form of digital, so that the storing of that data or information will becomes uh, less costlier than the analog form, and it is easy to transfer from one location to another location. Analog data cannot be shifted from one place to another place easily, but digital data, we can transmit that data or information from one location to another location in a nanoseconds or in a minutes. Suppose you are sending your email that is in digital form, it is immediately reached to the destination. And similarly, we can also process the given digital data in different form to get the different information. So this is the advantages of digital concept. So today we are trying to convert all information and data, even pictures, in form of digital, so that the cost will be reduced, and mm, processing time or sending time will be reduced. So three types of image processing is required or used. First is called optical image processing, second is analog image processing, and third one is called digital image processing. I'm not going to read this the definition of this optical image processing. You can read this, or you can take the screenshot of this optical image processing. In optical image processing, an optical image of the 3D object is its 2D projections that I have just discussed in the earlier page, which is the continuous 2D surface. These 2D projections hold 3D objects that are in focus. It also includes the study of the radiation source and other optical processes. This optical image is available in the optical form until it is converted into analog form, leading to the area of analog image processing. Then there is another concept that is called analog image processing. In analog image processing, we use different types of methods. First is, this is our analog image. It is converted into sampling. Then we convert this sampling into quantization, and after quantization, we get the digital image. So these are the steps to form the analog image processing, and notes are always asked on these topics. You may note that the image systems that use film for recording images are also known as analog image systems. In medical imaging, still films are used. In digital image processing, it relates to the field of using digital circuits, systems, and software algorithms to carry out image processing operations, which include quality enhancement of an image, counting of object, image analysis, and many more. Any digital imaging systems includes data acquisition, storage, manipulation, and transmission. First, we acquire the given object, and then we store that. After storing, we manipulate, or we do some processing. After processing, we send the original information that we get from this processing, and that information will be transmitted. Types of image systems and acquisition systems are as we do. First type of system is image systems, and it is divided into direct or active image systems, then indirect imaging systems, and this direct is also divided further in serial and parallel acquisition systems. So the meaning and definition about all these types are given in IGNOU block, and this is the figure from the IGNOU block. So you can study or read the meaning of this image system, direct or active image systems, from your IGNOU block. IGNOU block. Now we move to the sampling, because sampling and quantization are the main part of the image processing. So almost 50% topics or 70% topics of your block is based on this sampling and quantization. Sampling in image processing refers to the process of converting a continuous image into a discrete representation by capturing a subset of data points from the image. This is crucial for digital image processing. So it is the main part. As a digital systems work with discrete data. Here is a detailed explanation. These are the different explanation. First, concept of some sampling. Sampling involves selecting a finite number of data points from the continuous signal to represent the entire signal. For images, this means selecting specific pixels from the continuous space or possible pixel locations and intensity value that I have just discussed with the by the example of T. And then we use some sampling rate, and that rate is based on the different device capacity. And after that we use the types of sampling, that is uniform sampling. In uniform sampling we use two different: regular grid sampling and grid density. But in case of non-uniform sampling we use adaptive sampling. There is another way of sampling is aliasing and anti-aliasing. Aliasing means we increase the number of grids, and in anti-aliasing we remove the number of grids. Sampling theorem, there are different sampling theorem. First is called Nyquist theorem, and on this Nyquist-Shannon theorem there may be questions on this Nyquist-Shannon theorem. And this theorem says that the to get the correct or best image, the frequency of the image must be twice of the maximum frequency of the original object. So theorem states that no accurately sample or signal without aliasing, it must be sampled at a rate that is at least twice of the highest frequency present in the signal. If the signal frequency is 200, then you have to take the 400 frequency for the best sample. So this is the concept of Nyquist theorem, and Nyquist theorem is also used in our sound topics. For images, this means that the sampling rate must be sufficient to capture the highest spatial frequencies present in the image. Sampling in digital image, and for digital image we will use resolution, and it is nothing but the number of pixels. And image size, and image size means if we reduce the size, one square size image, two square size image, three square size image, so this is the size. And number of pixels in this size is called resolution. Sampling method, there are different sampling method: nearest neighbor sampling, bilinear sampling, bicubic sampling. And application of sampling is image resizing, image compression. If we convert the all data or image in a digital form, then we can resize that image according to our requirement, and we can store the data in less amount or less places. Practical consideration trades off. Then there is another type, quantization. Quantization in image processing is the process of mapping a large quantization in image processing. Generally there are questions based on sampling and quantization, so you must read in details or with carefully uh, about the sampling and quantization. Quantization in image processing is the process of mapping a large set of continuous intensity or color values into a smaller set of discrete values. This is a critical step in digital image processing and compression, enabling the representation and manipulation of images in digital systems. Here are some example concept of quantization. Quantization involves following key steps. First is discretization, and second is called representation. Discretization values are from 0 to 250, because 0 to 255 means it is 256. And I think you know, if we use 8 bits, so 2 to the power 8 equal to 256, such as pixel, because each pixel has a 8-bit information, and due to this 8-bit informations, it can range from 0 to 255 to a finite set of discrete values. Representation, there may be different types of representation. Quantization, grayscale, we can use a different type of concept. Generally in real life, we use some single color, some single color, that is called monotonic color. If we use a single color to represent the object, that is called monotonic. But if we use the single color with different intensity, that I have shown in the earlier pictures at this place, I have used the color black, but the intensity at this place is different. Intensity at this place is different. At this place is different. So if the intensity of the single color are varied, if the intensity of single color varied from 0 to 255, 0 to 255, then it is called gray color. Then it is called gray color. And if a single color with same intensity, this is our black color, and it has some intensity. If all objects are represented with this intensity, then we say that this is a monochrome color, or single color systems. But if single color is used with different intensity like this, then it is called gray color. And if object has different color, that is called multicolor, then we use multiple different types of color, like RGB. RGB is the main color of the optics, or in physics, you know, the all color can be formed with the help of this RGB. R red, G green, B blue. And there is another model that is called CMY, cyan, magenta, etc. And CMYK, then SHSI. We will discuss, or these topics are given in your block 3, I think. It is mentioned in block 3. So and questions are always um, arise on these topics, so you must go through that block. So this is the so quantization, bit depth, and this is the concept related to different color or image color. So representation quantization in grayscale image. If we use 8 bit, then it has 256 different values that just I have discussed. And if it is 1 bit, then only two different values are used, and that 0 is used for black and 1 is for used for white. So it is the monotonic color or simple color, single color concept. It has 256 different color of the single color, and 16-bit color that has 65,536 different grace value. For that, we use 16-bit color. So these are some topics that is discussed in block 3. Quantization in color image. This is our range division, then mapping, RGB model. Other model are HSAV, HSI, hue, saturation, value, etc. Then quantization error, due to some technical error, the storing or capturing the information from the image may be used in a wrong form, so there may be a quantization error. And that quantization error is one of the main quantization error is quantization noise. And how we will remove this noise, there are different algorithms, and the questions are all also based on this noise. Visual artifacts, quantization image compression, and the question is also based on compression technique, different compression techniques. First is called JPEG compression, second is lossy versus lossless compression, then quantization level. We will discuss in details about all these levels and in different algorithms. Just it is the overview that in quantization we will do all these things. So now we come to the place where we will find the sampling and quantization. How and which algorithm is used to find the sampling of any object, and how we will quantize that image in a mathematical form or in our real life for computer purpose. This is the concept. But now there is no time, so we will discuss this topic in the next class, so that we will learn in details about the image sampling and quantization. These two main topics are main topics of this image processing. Guys, please switch on your camera so that I can take images. Thank you, guys. We will meet tomorrow at the same time.
Thank you.